Hi, everyone. Welcome back. I'm sure if you were in Dean's breakout room for the first portion, you have already realized that he is a wealth of knowledge. I do want to introduce Dean formally, but I will also say that last night when I went to go write Dean's bio and think about introducing him, I've been working with him and interacting with him since 2019. And I think when we work with people all the time, we don't really think about all of the things they have done over time. And I was just in amazement of the amount of things that Dean has done. So Dean is joining us from Bradley University. He has been teaching there since 1998. He has a general interest in general and inorganic materials and environmental chemistry. You may have already had a chance to hear from him, but you'll hear from him more, and I hope access his resources for demos. He's in a wealth of knowledge for demos and also in student group activities as well. But I know today that he's going to share his work in going on a tour that connects with the theme of National Chemistry Week. So with that short introduction that doesn't even scratch the surface of all of you, Dean, I'm going to turn it over to you and give you the floor to share your story with us.
Thanks, Natalie. I think you must have looked up the wrong person. Okay, so I'm going to share my screen here. Let's see if I hit the right screen. Share. Okay, I want to be really super clear on this. This is that natural fiber welding is not my research. Okay, this was developed by a colleague of mine, Luke Haverhalls. He was started at the university several years ago, and he was taking his graduate work in fiber welding using ionic liquids, and he basically spun it into a company. I guess there was a pun intended there, but eventually he wound up leaving our school, and now he's the president of the company, Natural Fiber Welding, and he's pretty busy trotting around the globe and raising funds and stuff like that. But we managed to score a tour with Aaron Amstutz, who was one of the chief technological officers there, and happily for us, this organization, this company is just down the road from us. Okay, so he stayed in the Peoria area, and we visited their initial base of operations off the Bradley campus, and now are moving into about 4 different facilities as they expand. And so what I did was I grabbed a couple of my students who've worked with me before on various projects. That's me on the left in the picture, and then there's Caitlin, and Q is the one holding the camera there, and Zaman couldn't make it that day. But I said, hey, let's go on a tour of the place, and let's see if we can find out some information about solvent welding cellulose fibers, because National Chemistry Week is coming up. And so where I'm a bit restricted by I'm trying to move my next slide over here. Hold on a second here. Why is it not advancing? Oh, there we go. Okay, so I'm going to show you about some of the things we saw. I'm going to start with our own land use acknowledgement. Bradley University was built on the land of multiple Native nations. These lands were the traditional birthright of indigenous people who were forcibly removed and have faced centuries of struggle for survival and identity in the wake of dispossession and displacement. I'm going to acknowledge that our campus, Bradley campus, sits on the lands that were once home to the Peoria, Kaskaskia, Piankashaw, and Waya nations. We express honor to these indigenous people who we may have excluded in this acknowledgement due to erasure and historical inaccuracy. And I want to add that, yeah, we need to think about what we should be doing about this. And as Nim pointed out, there's a lot of different things that Beyond Benign has been doing to address this. Okay, so natural fiber welding got its start with what we call the Claris process. Okay, and in the Claris process, it involves using ionic liquids to solvent weld cotton yarn. Okay, And to get into this, I'm going to use some terms that I learned here. Let's think about cloth. Okay. Cloth is woven or knitted from yarn. Okay. And coming in, I had in mind the yarn that my mother works with, the real thick stuff. Okay. But even the yarn they're talking about is what I would call threads. Okay. And the yarn is itself is made from twisted fibers. Okay. And the fibers, in the case of cotton, contain largely cellulose polymers. Okay. If what they're trying to do is they're trying to take these fibers, and you can see the electron micrographs in this image here, of a yarn. You can see all the fibers, they look like strands of spaghetti, right? Okay. The idea is to take these fibers and solvent weld them so that the fibers sort of fuse together. Okay. And in the image on the right, what we have is a cross section of the yarn, and these were provided by Natural Fiber Welding for us. But if you look, can you see all the individual fibers towards the center of the yarn? But as you look out towards the edges, all the fibers are sort of merged together. Okay. And the idea is that this would still maintain that this is still cellulose, but because these fibers are sort of fused together into one continuous structure or a few continuous structures, it produces a much tougher, a stronger fiber and more something that's more abrasion resistant than the original yarns. Okay. And they've also found out that it has some very interesting moisture management properties. Cotton, as you know, is very water loving, right? And but by solvent welding some of these fibers in this yarn, you can sort of, in some cases, force water to move wick one way through the material and not go backwards. Okay. But when I look at this solvent welded fiber here on the end, it looks like what I call a spaghetti crystal. And, when you make spaghetti, and sometimes your noodles all stick together, right? And I use that in my materials chem course as an analogy for polymer crystals. And I call them spaghetti crystals. To me, that looks like a bunch of spaghetti all clumped together. What I was also thinking of this morning is if you've ever had a shoelace that's broken, maybe a nylon shoelace, and if you've ever taken like a lighter and used the heat from the lighter to sort of melt the ends of the shoelaces together so you can keep using the shoelace. I don't know if anybody ever does that, but that's what it kind of reminds me of as well. Only this isn't heat, this isn't melting, this is solvent welding. All right. So cellulose itself is a polysaccharide made from polymerized glucose. Okay. You can polymerize it one way and you can get starch, and you can polymerize it a different way, you get cellulose. All right. So this is a cartoon of the cellulose structure. Cellulose tends to be a linear polymer, and it tends to pack together very tightly. And it can be very crystalline in that regard. And it's less soluble than starch. Starch tends to be branched or sometimes helical. And so as an analogy here, I went into the backyard and I found some straight sticks and some branchy sticks. And you can see that the straight sticks bunch together a lot better than the branchy sticks. I think this also works for a good description of high and low density polyethylene. Okay, because high density polyethylene polymer strands tend to bunch together very well in a crystalline structure. Low density polyethylene tends to be more branched, and LDPE is often a bit more flexible than HDPE. Okay, but I just wanted to show you this as sort of the structure we're thinking of, because we're visiting an active company with lots of trade secrets. We all had to sign non-disclosure agreements. Okay, so there's a lot of things I'm not allowed to say that I'm just burning to tell you. Okay. But this is the ionic liquid. Thankfully, they let me share that. This is the ionic liquid that they use to do solvent welding. And ionic liquids are ionic compounds. But in general chemistry, when we talk about ionic compounds, we usually talk about relatively small cations and small anions, have a relatively high charge density. And the cations and anions are attracted to each other by electrostatic interactions. Ionic liquids are not really any different, except the anions and the cations tend to be large organic ions. Okay. And so they have a lower charge density, and they often have nonpolar functional groups. They're a bit greasier, if you will. And as a result, these ionic liquids have much lower melting points than inorganic salts. And many of them are liquids at room temperature, hence the words ionic liquid. Now, they are liquids, but they have enough attraction to each other through these ionic interactions. They don't release as much VOCs into the atmosphere as, say, many other organic solvents. And so there's an advantage to using ionic liquids. Ionic liquids also tend to be non-flammable. Okay. And even though they have all that greasy structure on the outside, because they have charges, they can interact very effectively with polar functional groups. For example, the OH groups, the alcohols on cellulose. EMM acetate, as this is called, is not cheap, $100 a kilogram. But on the other hand, that actually provides motivation for NFW to recycle this material. Okay. But it was chosen because it interacts very well with the polar groups of the cellulose molecules. Okay. And I should also mention, being an ionic compound, this is water miscible. Okay. So it can be washed from the yarn and very easily recycled. Now, what I really want to tell you is about the other thing they add. Okay. I can't even use the words that I wanted to use, but let's suffice to say they add a proprietary molecular additive. That's not my words, that's theirs. I'm like, molecular additive, what is that? That could be just about anything. But suffice it to say, they add something else to help the solvent welding process. Okay. And it is also recycled. I will reveal that molecular additive has an odor associated if you ever encountered it in its pure form. And they do such a great job of recycling this and keeping it contained. I only smelled it once while I was walking next to the lines. Okay, so they really, really work on recovering this material. Okay, so what we can do is we can connect this to a life cycle assessment. Okay, and this is my version of a life cycle assessment. I don't know, you can all offer corrections to it, but what I see is going on is we're starting out with carbon dioxide and water, and we're putting energy in. Plants are converting it into glucose, and they're producing oxygen as a byproduct in this case, pretty handy byproduct. But and the plants convert it into cellulose fibers, and that's where humans kind of drop in on the situation, and they start taking these cellulose fibers and turning it into cotton yarn. And as I go up this stack from the bottom of entries from the bottom up, I would submit that we're going into increasing order, okay, as we go. I also want to point out that we're putting energy in every step of the way. But we take these cellulose fibers and spin it into yarn, okay? And people have been doing this for a long time. Where natural fiber welding comes in is they solvent weld that yarn, okay? Where they take the yarn, expose it to the ionic liquid solutions. The ionic liquid goes in, sort of spreads the polymer chains, the cellulose chains apart from each other, gets them a bit sticky. They can interact with each other via hydrogen bonding. The ionic liquid, the molecular additive, is removed by water washing. Okay. And because of the cost of the solvents involved, and because they want to make sure this stuff is clean, they wash these yarns 4 times at least. Okay. And then they recover all of this ionic liquid, molecular additive in the water, and they basically go through a whole bunch of evaporation steps to separate the components back out from each other, and then put it back into the system. And there's very, very little waste produced. There's some impurities from the yarn that get washed out. My understanding is they've been in operation for for years, and they've maybe got less than a 5-gallon drum of this stuff. Is what I was told. Okay, it's very little waste produced in this process. Okay, but they have this solvent welded yarn, which again is a bit stronger than the normal cotton yarn. Okay, then it gets knitted. Okay, and I can tell you that the knitting machine was pretty spectacular to watch. Basically, the industry or the fabric industry is pretty well entrenched. Okay, and they had a hard time finding companies that were willing to take their knitting machines and say, hey, let's use this experimental yarn and knit some fabrics off of it. And so what natural fiber welding had to do was they had to get their own knitting machines, and I don't know, it was a bunch of spools feeding yarn into this sheet of fabric, which was growing and spinning round and round, and it was just pretty spectacular to watch. But they knit this into their fabric, which they call the Claris fabric. Okay, my question was, why not make the fabric first and then solvent weld the whole thing afterward? And the response was, well, if we did that, we wouldn't have a shirt that anybody would want to wear, because it would get too hard, it would get too rigid, it would be very uncomfortable to wear. So they have to solvent weld the yarn and then knit it into the fabric. Okay, but once you have the fabric, then you can make it into clothing. And don't have an extensive list of all the companies that are into this sort of stuff, but I know Ralph Lauren was a company that has really taken an interest in this. Okay, so once we have this, what do we do with it when we're at the end of use? What happens when the clothing wears out? Okay, obviously we're trying to avoid the grave. All right, we don't want to go from cradle to grave. We want to try and reuse as much of this as possible. And the game plan is to recycle as much as possible, break it down into the cellulose fibers and bring it back into making more yarn. But there is that composting option as well. It is cellulose, it is biodegradable. And here in the composting, what you have is eventual combination with the oxygen and bring it back down to carbon dioxide and water. And so that sort of completes the cycle. I want to point out, in every step along the way, we're pumping energy in, right? Except one. There's one exergonic step that I can see, and that's taking the cellulose from the waste and letting it combine with oxygen to produce carbon dioxide and water. Okay. Everything else puts energy in. So I haven't shown that in the life cycle analysis, but it certainly looms over that whole picture. All right. And a week or two ago, I was visiting a historic site, and I thought I ran into an older method of fabric recycling. Okay. This is more of a mechanical method, but what we have here is, have you ever seen these before? These rug looms? Okay. This is an old wooden loom with a whole bunch of strings on it. And what people are doing is they're taking, this is denim that they've cut into small strips. This is scraps. And basically that you take that little shuttle in the middle and you run it between the strings, and you have these foot levers, and you move the strings past each other and move the shuttle the other direction, and you move the strings back and forth. And by the time you're done, you're left with a rag rug. Okay. So this is sort of an old school way of mechanically recycling fibers. Okay. But what natural fiber welding is trying to do is to use chemistry to recycle things more at the molecular level, and really close the loop on this process. If we have, if we consider fibers that were petrochemically based, okay, polyethylene terephthalate, for example, or polypropylene or other fibers that you find in fabrics, all those are petrochemically derived. They're pulled out of the carbon's pulled out of the ground as oil, and a lot of this is using old carbon. The idea here is that if in this cycle with the cellulose, we're having stuff pulled out of carbon in the air around us, and we're using so-called newer carbon, right? And so it's a different approach to well, using our carbon sources. Problem is not only we have this polypropylene, the polyesters, these petrochemically derived fibers have different mechanical properties than cellulose. There are advantages to working with polypropylene. There are advantages for working with polyesters because of the way they interact with moisture, for example, or their strength. And for a while, cotton has not been able to compete at some of these levels. And so one of the points of solvent welding these yarns, solvent welding this cellulose, this cotton, is to be able to make yarn that is mechanically similar to these petrochemically derived polymers. Okay, so hopefully the goal is in the future to make fabric that behaves like polyester, polypropylene, but it's derived completely from cotton. And so that's the goal here. What kind of shirts can you make from these? Expensive ones. Okay. Most of the people there are kind of, the shirts are clothing is kind of experimental. And, some of the shirts are like $70. Okay. So nobody's running around wearing a lot of these. Okay. So it's going to be some time before we find this stuff on the shelves at Walmart. They send us some fabric samples here. And all I can do is I can just wave them up on my screen and stroke them and say, ooh, I can, they feel like fabric. My sense of touch is not that well refined, but this is hopefully a vision for the future here, making, again, more robust fabrics using this solvent welding. And so from an educational standpoint, we said, how can we show solvent welding in a classroom to a large group of people? Okay. And so what we did was, instead of using cellulose, we took some starch packing peanuts. Have any of you ever solvent welded starch packing peanuts? Starch is a little bit water soluble. Okay. We have 3 strands of packing peanuts strung on some just ordinary yarn. And I'll show you the video what we did here. We have the packing peanuts on the yarn, and you twist the yarn up like that, twist the strands. So each of these packing peanut strands represents a cellulose fiber, okay? And they just spin apart from each other, right? But if we twist them back together, and this time we hit it with some water. We'll speed this up a little bit. Elapsed time on this was maybe 2 or 3 minutes. Maybe give it a little help there, squeeze it together. We let it sit a little while for the packing peanuts to get sticky. And then we let go, and then the packing peanuts stick together. And so what we've done is we've taken starch-based packing peanuts on a string, and we've solvent welded them together. And this is an analogy to the solvent welding for the cellulose fibers in the yarn. After we put this blog post together, about the day after we did, I thought, hey, we don't need to run a needle and through these packing peanuts. All you have to do is skewer them on chopsticks. So take some chopsticks, some wooden chopsticks, skewer the packing peanuts on, and just put them side to side, and you can solvent weld them together that way as well. So this is a solvent welding analogy here. Okay. Another thing we've messed around with was using polylactic acid strands. So this is some PLA fiber or strands left over from a 3D printing project. And we can twist those little strands together and we can hit it with acetone, kind of hold it together for a little while, and they start solvent welding together. So this is another analogy you can use to that cellulose fiber welding. Okay. I wanted to show you a couple other things that, have I got a little time, Nim? Okay, awesome. All right. So this is National Chemistry Week and we're talking about fibers. Okay. And I wanted to tell you about an event that happened in Peoria 50 years ago, 50 plus years ago. Okay. It involves fibers, but it doesn't involve welding. Okay. And actually these sort of incidents would happen a lot more often across the United States. And it's the day the nylons ran in Peoria. So in June of 1970, there was a coal-fired power plant down by the Illinois River in central Illinois, in Peoria. And in this coal-fired power plant, it was producing ash as it was burning the coal. The local coal around here has a lot of sulfur in it, often present as the mineral marcasite, which is sort of like pyrite, but falls apart a little bit more easily. And they were burning coal, probably to help people run their air conditioners. And what was happening is the ash was falling out of the smoke plume and landing on the cars near the power plant, and it was discoloring the car paint. And it turns out this had happened before. Okay. People in the area near this power plant were also having headaches, and they were getting burning in the eyes. And then people's nylon stockings started to fall apart. Okay, I realize that people don't necessarily wear as many nylon stockings as they used to, but can you see the newspaper picture from the next day? Can you see the three sets of legs? Can you see how the nylon stockings are all falling apart? It's laddering or running. The nylon was disintegrating, and there was a lot of confusion, but what it was concluded, there was a lot of sulfur in the air, sulfur compounds in the air, sulfur oxides, and they were reacting on the surface of the ash. Ash was helping to catalyze the sulfur dioxide conversion to sulfur trioxide. It was interacting with the moisture in the air to form sulfuric acid on these ash particles. And when the ash hit the nylon depolymerized. And this was next to a department store where this happened. And so people were walking around at lunchtime saying, I can't go back to work looking like this. So they go back into the department store, buy a pair of nylons, stick them on, and then walk back out, and those would start falling apart. So it got ugly. And this is Bradley University lore here, because the power plant denied any wrongdoing, and they said, here's some nylon under our smokestack. You see nothing's happening. But one of our students from years ago kind of dug in on this and kind of was able to reproduce the conditions that showed that it was the power plant that was doing this sort of damage. Okay. And so in the corner of this slide, what you see on that Petri dish is a swatch of nylon fabric with a bit of, I think, 6 molar sulfuric acid on it. And you can see as it sits for a little while, decolorizes the nylon, probably because it's attacking whatever dyes are in there, but then it also tears the nylon apart. And you can take nylon fabric and just wipe it out this way. Okay. What we have done is we've incorporated this little experiment and a couple other experiments into a green general chemistry lab that we've been working on with Beyond Benign. It's called Polymers and Green Chemistry. We've also taken polystyrene and starch-based packing peanuts and used it to simulate microplastic transport of persistent organic pollutants. Okay, if you take both of these packing peanuts, a starch packing peanut and a polystyrene packing peanut, and you write on it with a permanent marker, and the permanent marker represents persistent organic pollutant, and you can put it in water, and you can see that the green ink sticks to the polystyrene packing peanut, and you can think about how microplastic can carry a persistent organic pollutant around into different places, using it's sort of like a vector for carrying those pops around. But if we have a starch-based packing peanut, you can color it up with a marker, put it in water, and it disintegrates. And so it's not able to transport those pollutants around. And so this is part of a lab that we've been working on with Beyond Benign. What I also have here is a list of some of the other labs that we've been working on, the greener gen chemistry labs that we've submitted and Beyond Benign will be putting out soon. Okay, so there's that. And another fiber thing I want to quick mention here. This past summer, I went to the Green Chemistry and Engineering Conference in Reston, Virginia. Okay. And if you ever go to Reston, it's really close to Dulles Airport. If you go to Dulles Airport, they have part 2 of the National Air and Space Museum. You get to see the space shuttle, which totally geeked me out. But what they also had there was a spacesuit. Okay. And they showed all the different fabrics involved in the spacesuit, all the different layers. Okay. The one that I thought was pretty interesting was the cooling garment, which was the sort of the long johns at the bottom level. You see all the tubes running through the garment. Okay. Now, it's fabric, so it ties into National Chemistry Week, but I should also say it's probably not very green. Okay. I find when I get some funding from the Illinois Space Grant Consortium and do some space related stuff, I find that there's not much of an intersection between green chemistry at this point, green chemistry and space chemistry. So I think that's an area that needs some work. And I'll just throw that challenge out there for everybody to think about. Who knows, maybe natural fiber welded products will find their way into spacesuits on down the line. Who knows? So I want to thank you for all your attention. If you want to take a look at the blog post where I talk about our little visit to natural fiber welding, there's a QR code. And I want to thank Beyond Benign and these other organizations for their funding. If you've got any questions for me, my email address is campbell@fsmail.bradley.edu. And thank you for your time.